Welcome to our lecture on igneous rocks, the first of three types of rocks that we'll discuss in this course. So the parent material of igneous rocks is magma, or more general, molten rock. And so molten rock is formed by the melting of rock that occurs beneath the surface, usually in the asthenosphere. And magma, when it reaches the surface, is known as lava. And magma can be completely or partially molten, meaning it can have some solid components. And so magma has three components: liquids, solids, and gases. So obviously the majority of the magma is liquid, and the liquid material contains the ions of the eight most common elements of Earth's crust: silicon, oxygen, aluminum, potassium, calcium, sodium, iron, and magnesium. There can be some solids present in the magma as well, and if so, those solids are usually silicate minerals that have crystallized out. And finally, there can be gases in the magma too. So dissolved gases in a liquid or solid are known as volatiles. And the most common volatiles or dissolved gases in magma are water, carbon dioxide, and sulfur dioxide. So magma can contain, and often does contain, all three states of matter in it. So how does magma turn into solid crystalline rock? Well, first, those mobile ions, they are very active while hot. That's why they don't bond together, and that's what makes the magma a liquid. But as the magma cools, those mobile ions, they begin to slow down and bond together. Now the first two ions that bond together are the silicon and the oxygen. So four oxygen atoms tend to bond with one silicon atom to form that silica tetrahedra that we discussed in our lecture on minerals. And then, upon that silica tetrahedra, other ions bond or accumulate, or the tetrahedra polymerize, which means those silica tetrahedra share one or more oxygens, and that forms different types of silicate minerals. So first, the silica tetrahedra forms, and then those tetrahedra either bond with other elements and or polymerize with other tetrahedra. So there are two ways in which igneous rocks form, and these are called igneous processes, and they form two different types of igneous rocks. The first is intrusive, also sometimes referred to as plutonic igneous rocks, and the second type is extrusive, also known as volcanic igneous rocks. Extrusive igneous rocks, they form whenever magma becomes stagnant deep beneath the surface. And it never reaches the surface, and it slowly begins to cool deep beneath the surface. And during that slow cooling, the molten rock crystallizes and solidifies into solid igneous rock. Extrusive igneous rocks, they form whenever magma reaches just beneath the surface or to the surface as lava, where it is much cooler, resulting in the molten rock cooling more rapidly. And that more rapid cooling and crystallization of molten rock forms extrusive igneous rocks. So intrusive igneous rocks are formed from the slow cooling of molten rock deep beneath the surface, and extrusive igneous rocks are formed from the rapid cooling of molten rock at or near the surface. How can you tell the two apart? Well, intrusive igneous rocks, because they form from the slow cooling of molten rock deep beneath the surface, there was a large amount of time for mineral crystals to grow. And as a result, intrusive igneous rocks have very large, coarse mineral crystals. As you can see in this piece of granite, you can visibly see these different mineral crystals all grown together. And if you find intrusive igneous rocks at the surface, that means that weathering and erosion must have removed all the rock that was once over top of them to bring them to the surface, because remember, they form from the slow cooling of molten rock deep beneath the surface. So some locations which you could find intrusive igneous rock, which is very common, but just some are, say, Mount Rushmore in the Black Hills of South Dakota, Mount Washington in New Hampshire, or Yosemite Park National Park in California. The faces of the 4 presidents in Mount Rushmore are carved into granite, an intrusive igneous rock. So this rock right here, it formed from a large volume, as you can see from how big this granite face is, a large volume of molten rock deep beneath the surface that slowly cooled and crystallized. And since it's at the surface now, that means that all the rock over top was eroded away, exposing it. Extrusive igneous rocks are different from intrusive because they have a fine-grained texture, or produced by very small mineral crystals. These small mineral crystals form because the molten rock cooled very quickly, too quickly for large mineral crystals to form. In these extrusive igneous rocks, the mineral crystals are so small that unlike in intrusive igneous rocks, you cannot discern them one from another with the naked eye. That's how small the mineral crystals are. So where you could find extrusive igneous rocks is usually anywhere where you have volcanism, like the Cascade Mountains, Hawaii, Andes, or the Aleutian Islands. Cascades, the Andes, and Aleutian Islands all being subduction zones, and Hawaii being a hotspot. All have volcanism. So here, this lava flow from Kilauea in Hawaii, it's cooling rapidly at the surface to form the extrusive igneous rock basalt. So now we're going to look at the chemical composition of igneous rocks. So igneous rocks are composed of silicate minerals, and we learned in our last lecture that there's 2 types of silicate minerals. There's the dark ferromagnesian silicates and the light non-ferromagnesian silicates. The ferromagnesian silicates, the dark silicates, are rich in iron magnesium, dark in color. They have comparatively low silica content compared to the light silicates. And the major groups of ferromagnesian silicates include olivine, pyroxenes, and amphiboles. The light non-ferromagnesian silicates are rich in potassium and calcium and sodium, but poor in iron and magnesium. They are generally light in color, and they are comparatively high in silica, so they have more silica in them than the ferromagnesian silicates. And some common non-ferromagnesian silicates include quartz, muscovite, and feldspars. So now we're going to look at different composition of igneous rocks. The first is felsic, sometimes known as granitic. Felsic igneous rocks are about 70% silica, and they are the largest constituent of the continental crust. So the continental crust is composed of felsic igneous rocks. Felsic igneous rocks are generally light in color, and they're lower in density due to the low iron magnesium content. So as you might be able to tell, felsic igneous rocks are composed predominantly of non-ferromagnesian silicates. And before we go any further, I just want to point out that the intrusive or extrusive igneous rocks, that's determined by how the rock forms, and in other words, how rapidly the rock cools and what sort of texture it develops. The chemical composition of the igneous rock is completely independent of whether it's intrusive or extrusive. Sometimes students get intrusive, extrusive, and the different chemical compositions intermingled, but chemical composition and intrusive or extrusive, those are completely separate from one another, independent of one another. So, sorry for that little interlude, but so felsic igneous rocks, you can see in this chart, in the column on the far left, we have the different minerals, and on the left, on the y-axis, on the left-hand side, we have the percent by volume of different minerals that make up a felsic igneous rock. So any rock that falls within this range, in this column, is felsic, and you can see at minimum, I should say,
it's 9:30.
They have about 25 to 30% dark ferromagnesian silicates. Okay, so the minimum amount of non-ferromagnesian silicates that felsic igneous rocks have is about 75%. So they can go anywhere from 100% non-ferromagnesian to 75% non-ferromagnesian. And so felsic igneous rocks contain muscovite, quartz, a lot of potassium feldspar, and sodium-rich plagioclase feldspar. Remember, plagioclase feldspar is a feldspar that either has sodium or calcium. And then as far as the ferromagnesian silicates, it contains biotite and some amphibole, usually hornblende. Remember, hornblende is the most common mineral in the amphibole group. Okay, so mostly light non-ferromagnesian silicates in felsic igneous rocks. That makes felsic igneous rocks generally light in color too. Then we have mafic, also sometimes referred to as basaltic igneous rocks. These igneous rocks are about 50% silica. They're denser than felsic rocks. They're the main constituent of the oceanic crust that compose the seafloor. They're generally dark in color and rich in iron and magnesium. As you might guess, mafic igneous rocks are composed mostly of ferromagnesian silicates. Thus, their dark color and their richness in iron and magnesium. So if you see in this column over here, we have mafic igneous rocks, and they have mostly dark ferromagnesian silicates. So olivine, pyroxene, which is mostly augite, the most common pyroxene, and then amphibole, which is hornblende, the most common amphibole, and then they tend to have calcium-rich plagioclase feldspar. And plagioclase feldspar is really the only non-ferromagnesian silicate found in mafic igneous rocks. Then we have the composition that is in between felsic and mafic, and that is intermediate, also sometimes referred to as andesitic composition. Intermediate is about 60% silica, which is less than the 70% felsic has and more than the 50% mafic has. And they're about 25% dark silicates. They're not light, they're not dark, they're generally grayish in color, and they get their name from andesite. Andesite is the most commonly found igneous rock with an intermediate composition, chemical composition. And intermediate igneous rocks are mostly found around volcanic activity along continental margins, like the Andes or Cascades. So basically around volcanoes along subduction zones where oceanic lithosphere is subducting under continental lithosphere. That's where we find a lot of intermediate igneous rocks. So right here in between felsic and mafic, we have intermediate igneous rocks. You can see they're kind of half and half. Half non-ferromagnesian and half ferromagnesian. Okay, so they contain quartz, a little bit of quartz, a little bit of potassium feldspar, a mix of sodium and calcium-rich plagioclase feldspar, a little bit of biotite, a lot of hornblende, and some augite. So that's makes intermediate igneous rocks, and right in between. And then finally we have ultramafic igneous rocks. Ultramafic igneous rocks about 40% silica, so the least amount of silica, extremely rich in iron and magnesium, which makes them very dense. And ultramafic igneous rocks, I included them last because they do not naturally form in the crust, on the crust. They are the main constituent of the upper mantle. So ultramafic rocks are mantle rocks. So if we find them at the surface, that's because they've been brought here by volcanism. They do not naturally form in the crust. So ultramafic igneous rocks over here on the far right, they are mostly ferromagnesian silicates, mostly olivine and some augite, pyroxene, and what little non-ferromagnesian silicates it has is extremely calcium-rich plagioclase feldspar. So you'll notice that felsic igneous rocks have plagioclase feldspar, intermediate igneous rocks have plagioclase feldspar, mafic has plagioclase feldspar, and ultramafic has plagioclase feldspar. They all have plagioclase feldspar. The difference is how much sodium or calcium is in the plagioclase feldspar. Felsic has more sodium-rich plagioclase feldspar, and mafic and ultramafic have more calcium-rich plagioclase feldspar. So now we're going to look at the silica content in magmas and how that influences the magma. So felsic magmas, they have about 70% silica, and on the other end of the spectrum, ultramafic igneous rocks have about 40% silica. And so in general, the more silica an igneous rock has, the less iron, magnesium, and calcium it has, and the more sodium, potassium it has. So that'd be felsic. And the less silica the igneous rock has, the more iron and magnesium and calcium it has, and the less sodium and potassium. That'd be more mafic. And the amount of silica in the magma influences the behavior of the magma, mainly its viscosity. So what is viscosity? Well, if you're not familiar with viscosity, viscosity is the internal resistance to flow of a fluid. If you go onto Blackboard, you can download these PowerPoint slides and click this hyperlink and watch this demonstration, which shows how water, a fluid with low viscosity, flows very easily, where corn syrup, a fluid with a much higher viscosity, has much more resistance to flow. Okay, so you can think of honey having a high viscosity and water having a low viscosity, because honey resists flowing. Right, so felsic magmas, they are quite viscous because they have a lot of silica, and they can erupt at temperatures as low as 700 degrees centigrade, and because of their viscous nature, felsic magmas often lead to explosive eruptions. So this video on YouTube, if you click the hyperlink, just shows a little example of an explosive eruption. Mafic magmas, on the other hand, being less viscous, and they erupt at temperatures much higher, 1100 to 1250 degrees centigrade, they often lead to effusive or peaceful eruptions. So this video is some like an effusive or peaceful eruption of in Hawaii, where we don't have any explosions, we just have lava kind of spewing out, like a water fountain kind of. So you can download the PowerPoints and look at this hyperlink as well. So now we're going to look at some igneous textures. So the texture of igneous rock is the way the rock looks and feels. This is mainly determined by the size of the mineral crystals, and sometimes even the lack of the mineral crystals, and even other features like gas bubbles. So the different igneous textures that igneous rocks possess are Aphanitic Texture, that's the fine-grained, the small mineral crystals. Phaneritic Texture, that's the coarse-grained texture, large mineral crystals. Porphyritic, Pyroclastic, Vesicular, Glassy, and Pegmatitic. And we're going to look at each one of these and find out how and where they form. So first, Aphanitic texture is produced whenever lava cools quickly on the surface, or magma cools quickly near the surface. And so the magma cools quick enough that very, very tiny mineral crystals form. And so these mineral crystals cannot be discerned with from one another with the naked eye. And so there's very, very, very fine texture. And that's what makes an aphanitic texture. So extrusive igneous rocks often have an aphanitic texture. Phaneritic texture is produced when magma cools slowly at deep beneath the surface, allowing for large, coarse mineral crystals to develop. So phaneritic texture belongs to intrusive igneous rocks, where we have these large, coarse mineral crystals. Then we have porphyritic. Porphyritic texture is kind of a combination of both intrusive and extrusive processes. First, the magma begins to cool slowly, which during that time large mineral crystals form, which you can see here. They're called these phenocrysts, these large mineral crystals. These phenocrysts right there. And then the magma becomes mobile. It reaches near the surface, or to the surface, where the remainder of the melt rapidly cools, forming very tiny mineral crystals called the ground mass. So porphyritic texture is kind of a combination of both, and is the result of slow and then rapid cooling. Next we have Pyroclastic Texture. So Pyroclastic Texture, the name Pyroclastic meaning pieces of fire, pyro being fire and clastic being piece, is produced whenever debris, volcanic debris, so of magma and rock, during explosive volcanic eruption are fused together. So pyroclastic igneous rocks often look like little tiny pieces have been fused together, and it's much softer than other igneous rocks, and you can rub it and some pieces can flake off. So pyroclastic igneous rocks form where there is explosive volcanism. Next we have vesicular texture, and a vesicular texture occurs whenever molten rock, usually at the surface, is formed of lava, cools rapidly enough that gas bubbles that are in the lava are preserved. You can see these little tiny bubbles in here. So whenever those gas bubbles are found in the rock, giving these little vesicles, we call that texture the vesicular texture. Next is a glassy texture. The glassy texture develops whenever the molten rock cools so rapidly that the mobile ions do not have time to arrange themselves into crystals, and they just freeze right in place randomly, and that forms glass. So volcanic glass, also known as obsidian on the right here, and pumice on the left, they do not have crystalline structure. They don't contain crystals. The material just kind of freezes right in place, giving it the glassy texture. Sometimes pumice is mistakenly said to have a vesicular texture because it does have these little gas bubbles. What makes it glassy is the lack of any mineral crystals. And finally, we have a pegmatitic texture. Pegmatitic texture is whenever the igneous rock has extremely large crystals that are abnormally large, larger than 1 centimeter in diameter. And this occurs whenever there are significant amounts of volatiles, dissolved gases in the magma that can allow for these large mineral crystals to develop. That's a pegmatitic texture. So the texture of the igneous rock can tell us something about how the rock formed and what's going on. So if we find an igneous rock with a phaneritic texture, like this one right here, that tells us that that igneous rock formed from the slow cooling of molten rock deep beneath the surface. If we find an igneous rock with porphyritic texture, that tells us that the rock started cooling at depth where these large mineral crystals formed, and then the magma made it to the surface, or near the surface, where the remaining of the melt rapidly cooled, forming the small mineral crystals. Aphanitic texture, this tells us that there is most likely volcanism, that molten rock erupted to or near the surface, where it rapidly cooled, developing this fine-grained texture with small mineral crystals. Pyroclastic texture tells us that there's most likely explosive volcanism, where there is a large amount of energy present to fuse these fragments of magma and rock together. And finally, the glassy texture also tells us that we have very rapid cooling of molten rock, usually flying through the air. That's what causes it to cool so rapidly. So once again, glassy texture tells us that it's probably explosive volcanism.